Hi, this is Dave Johnson. Welcome to another edition of Math Off Topics. Today I want to talk about the Zero-Bounded Limit Theorem, which is a limit theorem that doesn't appear in all calculus textbooks. Oftentimes you can work the problem without that particular theorem because you can use maybe the squeeze theorem or something else. But I think the Zero-Bounded Limit Theorem is very powerful and it's pretty simple to apply. And it even works in situations where other theorems might not work. In fact, today I'm going to do an example um, where you cannot use L'Hopital's rule. I think a lot of students believe that L'Hopital can do any limit, but we're going to see today that is not possible. So let's get into it. First, I want to state the theorem. I'm not going to prove it. Textbooks that do have the theorem will mention that the theorem can be proven using the squeeze theorem. Basically, what it says is given an interval, and let's just walk through this, let's break it down. So, given an interval, uh, and it's going to be an open interval from a minus delta to a plus delta. So, we see here on the x axis an open interval, open because it doesn't include the endpoints. Delta is just some small, usually small quantity. Uh, in this case, delta is greater than 0. So anywhere from a minus delta to a plus delta. Okay, here's a. So given that interval, let's define a function b of x and say b is bounded on I. Now, what does bounded mean? Well, it means that the function doesn't go to, say, positive or negative infinity on the interval. Doesn't even have to be continuous, I believe. And let's suppose that there's another function, g of x, such that the limit of g of x as x approaches a is equal to 0. Then if both of those conditions are true, then the product of those two functions, b of x times g of x, so the bounded function times the function with a 0 limit, if you take the limit of that product as x goes to a, then that will equal 0. Now, again, this only works if the limit of g of x is 0. If it's some other limit, then this theorem doesn't apply. It turns out that g of x does not have to be defined at x equals a. It just has to have a limit at x equals a. And in fact, a can be it can be infinity, as you'll see in the example that I'm going to do in a moment. Okay, again, let's just look at the graph here. So here's our g of x. It has a limit of 0 at x equals a. So this is your g of x. Your b of x is your bounded function. I'm showing that it crosses the x-axis. It doesn't have to cross the x-axis. And it doesn't have to be 0 at or near a. All it has to be is bounded. In other words, not going to positive or negative infinity. Okay, so the example that I want to do, and we'll come back to the statement of the theorem as we need it, but let's do this limit as x goes to infinity of e to the x plus sine x in the numerator divided by e to the x plus cosine x in the denominator. And it's obviously indeterminate. So as x goes to infinity, e to the x goes to infinity. And so you get infinity divided by infinity, which is indeterminate. Now, if you've seen any of my other videos, you know that I really prefer, if possible, to do these limits without L'Hopital, especially early on, because you may not know differentiation, you may not have seen L'Hopital's rule yet. You want to get in the habit, if possible, of using algebraic approaches to solving these limits. It's good exercise. Okay, so this limit is an infinity over infinity indeterminate form. But let me just mention, if you do L'Hopital on this, then derivative of e to the x is e to the x, and derivative of sine x is cosine x. So you'll get e to the x plus cosine x upstairs, and downstairs you'll get e to the x minus sine x, which doesn't help at all. And you can do that over and over again, and L'Hopital will not make progress on this problem at all. So you're going to have to come up with a different way of doing the problem. Okay, so how are we going to do this? Well, my first step would be to say, let's factor out an e to the x from the both the numerator and the denominator. So limit as x goes to infinity, and we'll put an e to the x out here, get a 1 plus. Now, there was no e to the x multiplying the sine x, but I can write this now as e to the negative x sine x. And we'll come back and see why that's true. Let me just go ahead and do the denominator, do the same thing downstairs. And we get 1 plus e to the negative x cosine x. Now, this is true because if you multiply it back out, so e to the x times 1 is e to the x, e to the x times e to the negative x is just 1, and you get back your sine x. And this is true also downstairs. E to the x times 1 is e to the x. E to the x times e to the negative x is 1. So e to the 0, which is 1, times your cosine x. So you can factor it this way. It's perfectly legal to do that. Okay. Now, when you factor it that way, now the e to the x is canceled. And you've gotten rid of your indeterminate form. So equals limit as x goes to infinity of 1 plus e to the negative x times sine x divided by 1 plus e to the negative x times cosine x. Okay, so let's go ahead and move the limit into the fraction. So the limit of a quotient is the quotient of the limits. So I can write this as limit as x approaches infinity of 1 plus e to the negative x sine x divided by limit as x approaches infinity of 1 plus e to the negative x times cosine x. Well, of course, the limit of 1 is 1, and now we have to figure out what the limit of the e to the negative x sine x is. And also downstairs, limit of 1 is 1. And we have to figure out what limit as x goes to infinity of e to the negative x cosine x is. So let's take those problems off to the side for a moment. And let's do the top one first. So limit as x goes to infinity of e to the negative x times sine x. Well, this one is an example of a problem that can be done with the zero-bounded limit theorem. Why is that? Well, because the limit of the e to the negative x is 0 as x goes to infinity. E to the negative infinity is 0. And sine x is always bounded. So even though the limit of sine x as x goes to infinity is undefined, does not exist, sine x is bounded. So as far as our theorem is concerned, we've got our bounded function times our function that has a 0 limit. And so we can go ahead and say that the limit of this is 0. And likewise, the limit as x goes to infinity of e to the negative x times cosine x is also equal to 0 for the same reason. The e to the negative x, its limit is 0, and cosine x is bounded. Why do we say those functions, sine x and cosine x, are bounded? Because the range of sine x and the range of cosine x is -1 to 1. So inside, so for all x, the y value does not go outside of the range -1 to 1. So those functions are bounded. So by the zero bounded limit theorem, these these limits are 0. So let me just kind of put this aside for the moment. And so I can write the result here, the limit of 1 plus, so this would be 1 plus 0 upstairs, and then the limit of 1 plus the 0, so 1 plus 0 downstairs. We get 1 over 1, which is 1, and that's the answer to our question. So I hope this has been helpful. And if you enjoyed the video, please like and subscribe. And I look forward to seeing you next time.